This is a lesson on the basics of torque in calculus-based mechanics. I'm going to talk about just how to calculate torque in a calculus way. I'm leaving how to apply that in conjunction with Newton's second law for rotational dynamics for another lesson. Before we get moving anywhere, I wanted to remind you about how to calculate a cross product using the definition of a cross product, right? So torque is a cross product. If I take two vectors, A crossed into B, and we can see that over in the picture here, I can find the magnitude of it pretty easy if I know the magnitude of the vectors and the angle between them, but that's not what we're interested in for this situation. What we're interested in for this situation is to use the cross product, A crossed into B, and looking at the different components of A and B. And note that I have over here, if you take the determinant of this 3x3 matrix of the ijk vector and the two other vectors that you're taking the cross product of, that will allow you to figure out the different terms in the cross product here. And I'm going to follow up in the example. One thing I want to take from this slide, though, is to remind you about the cross product. When I look at crossing two vectors, when I cross A into B, the result is a vector pointing in the direction perpendicular to the original plane of the two vectors. So when we do this, we definitely need 3 dimensions, and we need to keep the right-hand rule and cross product in mind in that regard. Okay. So also in a prior lesson in the basics of classical mechanics, I just introduced the definition of torque. Torque is the rotational equivalent of force, and like I mentioned, we're going to use that with Newton's second law with rotation in another lesson. We have a point P. It's always, torque is always in reference to a pivot. So make sure when you're looking at these problems, you've clearly determined your pivot point. And like I mentioned before, we are going to do a cross product and use the right-hand rule for the direction, and the units are Newton meters. So without any further ado, I have a problem for us, torque as a cross product. Use the cross product to calculate the magnitude and direction, okay, interesting, of the torque of a force. So the force is given, applied at the position, and let me put units in here for the radius vector here. We'll assume it's in meters. Okay, so they give us nicely the components for each of these, but then it says it wants a magnitude and direction. So I see a little bit of work going on there in order to get a magnitude and direction. But initially, just finding the torque vector is going to be the radius vector. Okay, so please note that the order matters here for cross product. R crossed into F is not the same as F crossed into R. There'd be a negative sign in that situation. So we need to make sure to do this in the correct order. And so we're going to take the 2, -5, 6 vector and cross it into the 4, 7, -2 vector. Okay, and you can use the equation, the formula that I had put on the cross product slide. I'm going to remind you how to do a determinant in this situation. Remember I mentioned you can do the ijk vector and find the determinant of a 3x3 matrix where I put the r vector in here, 2, -5, 6, and the force vector 4, 7, -2, and find the determinant of that matrix. Okay, so hopefully you're in calculus far enough that you know how to find the determinant of a matrix. If I want to find the I component, I'm going to find the determinant of the small matrix, -5, 6, and 7, 2. Those components, I'll find the determinant of that matrix in the I hat direction. Okay, and I'm going to play the same game when I'm looking at the other two. I have to subtract off the j component, so that'll be 2, 6, 4, -2 in the j hat, and then I'll add on the determinant of the 2, -5, 4, 7 vector or matrix in the k hat direction. Okay. So if you're following with the formula on the cross product page that I showed you, we're going to cross multiply these together. So I get negative 5 times 2 is negative 10, and then I'm going to subtract off 7 times 6, which is 42, and that'll be in the I hat direction. I'm going to play the same game, negative 4 minus 24 in the j hat direction, and then I'll get 14 minus a negative 20 in the k hat direction. And so the torque here simplifies very nicely. I get a negative 52 in the I hat minus a negative 28 in the j hat, and then plus 34 in the k hat direction. So this would be the torque in the just in x, y, z, right? I could write it as a negative 52, 28, 34, right? Okay, so if you're following along at home, notice that I have made a copy error here. There's a negative 2 here, so there's a negative 2 here, and when I multiply those together, that's a positive 10. So in this position, I should get a negative 32. Do you see that? That's a negative 32, and that should be a negative 32. So catch your mistakes with your negative signs. Okay, so that's the vector in space. I can easily find the magnitude of this torque. I'm just going to go back to Pythagorean theorem, negative 32 squared plus 28 squared plus 34 squared, and I can take the square root of that. That'll equal the square root of 2964. I did not do that in my head. Please don't think I did that in my head. The magnitude of the torque, we're going to get 54.443. And the units on torque is Newton times meters. Okay, so that would be the magnitude. So we found the magnitude. Let's look at the direction here. We have a vector in 3 space. So let me draw some coordinates here in 3 space. So let this be the y-axis and the x-axis and the z-axis. I'll just draw the y-axis. You may see here in a second why I do that. I want to simplify drawing. So if I start at the origin, the torque is going to be a negative 32 in the x direction. Great. And then I'm going to go up a positive 28 in the y direction. And then in the z direction, if you imagine there's a z-axis here, right? Then the z is going to be a positive 34. So I'm going to come out here a positive 34. So when I draw the resultant torque vector in space from the origin, right, from head to tail, so it's going to look like this. Okay. And so when I look at this vector, let me do this. It extends down 28 in the y, and then this is the component. This is the resultant in the xz plane, right? So it goes out in the xz plane and then up 28. So we're finding we found the magnitude of this green vector, right? We know how much that green vector is, but we need to find a direction. And so it looks like here we need to define 2 different angles. I'm going to define 2 different angles. There's going to be an angle with respect to the negative z-axis here, which I'm going to call alpha. And also, there's going to be another angle here. Let me pick a nice color. Purple, that's a good. So that's from the x-axis. And then there's another angle from the resultant vector in the xz plane up to the total resultant vector. Okay, so I'm going to call that beta. Okay, so when we're looking at these 2 different vectors, 2 different angles, I can figure out, for instance, alpha. I'm going to say tan alpha is going to be the ratio of, remember this is y, this is x and y, right? We have a y component here. It's going to be the y component over the x component. I don't think that should surprise you. I'm sorry, the z component over the x component. Opposite over adjacent. This is the z plane. In the z direction, I have 34. And in the x direction, it's a negative 32, but I'm just going to put a 32 in this equation because I've already defined alpha to be from the negative x-axis. So 32 here. And when you run that through your calculator, you get alpha is 46.7357 degrees from the negative x direction. Okay. And then when we look at beta, beta is measured upward from the xz plane in the y direction. So I'm going to say tan beta, the opposite is going to be here, the y component. So the y component is definitely a 28. Let's see, the adjacent leg to beta is going to be this resultant vector in the xz plane, which I know will be 32 squared plus 34 squared, right? Those were the two components I used to find alpha. Those are the two components of this triangle in the xz plane there. So I'm finding the hypotenuse of that. So it'll be the square root of 32 plus 34 squared, 32 squared plus 34 squared, sorry. So when you do that and run that into your calculator, you get beta to be 30.951 degrees. Okay, so as defined on my picture here, I think you need to include the picture in order to properly do this. So that would be the magnitude and the direction in for solving for this torque. And notice this is about the pivot point of the origin. I never really specified that, but I think the problem I don't know. I guess maybe I would say that this is the point R in space, right? This is the origin is, let's see, 2, negative 5, 6. If I drew this properly, okay, so if this is the xy and this is the origin, okay, xy origin, the R is going to be at positive 2, negative 5, positive 6. So it's off in space somewhere. That's the radius vector. And the force is being applied at some angle from there, 4, 7, negative 2. So like off in this direction. So the resultant torque vector, and you can see that on the diagram, is going to be this thing pointing off, right? This is the resultant torque vector. I don't need absolute values there. That's the resultant torque vector, perpendicular. Notice that it's perpendicular to the plane of the radius vector and the force vector as I've drawn in the coordinate system here. So hopefully that gives you a little bit clearer idea of how these vectors are oriented in space and how the torque vector relates to both of those.